9.3, test about a mean. It's all the same, but not at all. Alright, because we're dealing with mean, I'm guessing we're going to use t instead of z, because it was meant to be. Alright, sorry. It's too early for this. Let's go. We're going to learn how to state and check conditions. We're going to calculate our standardized test statistic and find a p-value. We're going to do a significance test, and you make conclusions for two-side tests, and we're going to interpret the power. We're going to do power. We won't do power right now. All right. We're going to jump right into this, y'all. So if we are carrying out a significant test for mu, for our mean, we have to check the same conditions we used to do for intervals. It has to be random. It has to be less than 10% of the population if you want standard deviation to work. It has to be random if you want a good sample. And it has to be normal for us to use our tables and our calculator to find this stuff. So we can do that if the sample's over 30. You can say this if it doesn't have skew in your sample, and you can do this if the population is normal. All the same stuff we've done before. If you didn't get it before, you best learn it now. Alright? So I'm going to go relatively quickly through that slide. That should be old hat. That's in your plan, right? Whoa, my face! Move away. Now, for normality, if it's not over 30, and if it doesn't say population is normal, you have to sketch the graph on your paper. Okay, you can plug in the data in your calculator and make a comment like, hey, there's no outliers, or it does not appear to be skewed, so it's the sample is normal, so we can continue on with our test. All right. B batteries, more batteries. So this time, we're looking at the lifetime in hours of 15 AAA batteries from this random sample. We're going to check the conditions to see if we can do a significance test on this. Well, first off, it was a random sample. That passes. Secondly, 15 is definitely less than 10% of all AAA batteries. Unless they're a very small company. And they're like, we're going to use half our batteries. And they talk like that for some reason. Next, we need to see if it's normal. Well, it doesn't say the population is normal, and the sample's less than 30. So we need to graph it and see. When we dot plot it, there's no strong skew or big outliers. Okay? So we are good to go. Again, random, passes 10%, shows no skewedness. Okay? Guys, please take your time as you go through this video. Some of you who rush through it, they say you don't know what's going on. I rush through it. You shouldn't rush through it. Alright, to find our standardized test statistic, which in 9.2, when we're looking at proportion with z, is the same formula. So stat minus parameter over standard deviation. Same thing as our z-score. Been doing this a lot. Data you find minus what you believe over the standard deviation of what you... No, I don't want to restart. Restart tonight. Yeah. Yeah. Ta-da! We want to use z, but we can't. Because we know from last chapter that z is not accurate when you're dealing with mean. So, we are going to use t again. Some ice tea. The shame in my soul. We're going to use t. Okay? Z just isn't accurate enough for us. Okay? I'm going to sneeze. So this is our specific formula for mean. Our statistic minus our null hypothesis over the standard deviation of the sample this time over square root n. All right? Oh, that sneeze made me really congested. Hold on. I'm back. Hey, why did I ever use this pen tool? Is it decent? Huh. It's not. I'll try it later. Alright. Up my eyes because I'm sleepy. Alright, so when we perform this, again, we're going to be looking at degrees of freedom, just like we did with our confidence intervals. And our degrees of freedom is n minus 1, right? So we take our sample size, subtract 1 to find our degrees of freedom for t, because that's important. Now, as you change degrees of freedom, it actually changes how spread out your t distribution is. At 2 degrees of freedom, it's more spread out. At 9 degrees of freedom, it's tighter and closer to the normal distribution, which makes sense. The bigger your sample size, the closer you are to normal. Okay? So that's why we want big sample sizes. All right? It's still bell-shaped. All that's the same. The big thing is that we're using t, not z. There's more variability to t because with mean there's more funky stuff that can happen. Yeah, I just said this. I just said that. Now, you can use table B for this, but I'll be honest, we probably won't very often. Here's why. Alright. So let's say we're looking at the batteries, right? Our null hypothesis, we think it's bigger, we want it to be bigger than 30, right? So we're going to assume it's 30, and then let's do our test. With the actual stats we had in that battery example, with all those numbers, the mean of it was 33.93. Our null, why am I not using this? Our null was 30. Our statistic sample standard deviation was 9.82. And a black highlighter, that's ridiculous. Let's use this highlighter. And our sample size was 15. So when we find t, we got that to be 1.55. Okay? Look how colorful this is. Our degrees of freedom is 15 batteries. 15 minus 1 is 14. Okay? So when I look at table B, I go to my degrees of freedom, and I find 14. And then I'm looking for 1.55. Now 1.55 is in between those two numbers. So my p-value, I can't say for certain it's this. I can just say it's between 0.1 and 0.05. Not super accurate way to do it. So there's a better way to do it. Okay? So again, I found my t, found my degrees of freedom, and saw where it fell between. And then my p is between those two, right? Face. Alright? There's limitations. I told you it's not very accurate, right? It gives us an interval. It never gives us a specific p-value. It gives us enough to accept, reject a lot of the time, but it gets even worse when we have different degrees of freedom. So remember, with degrees of freedom, you always round down because that makes it more accurate, more conservative of an estimate. All right. Always round down with degrees of freedom. Suppose we want to do a test with our null hypothesis and alternative hypothesis, our significance level. We have a sample of 37, and we get our sample statistics 4.81, standard deviation is 0.365. The conditions are met. So why do we have some evidence for the alternative? Because our sample mean didn't equal our null hypothesis, right? So because our sample mean didn't equal our null hypothesis, maybe it's not true. That's the first. Most people just say, well, it's not 5, so that's the answer. But let's see if that's actually significant. Let's find the standard statistic and the p-value. Okay. State is up here. Our plan is told right there. It works. Let's find our stuff. All right, so to find our t, we're going to do our x bar minus our mean over our s of x over square root of n, right? So my x bar was 4.81 minus 5 over 0.365 over square root of 37. Okay? When I do that, let's see what I get. I'm going to do this all solo. You guys get to watch me do math. If I knew what I was doing. That's not right. Can't be right. Oh. Oh my gosh. My neck does not feel good today. I got negative 3.17. So that's my t. That's my test statistic. Now, I could use my chart and go my degrees of freedom, go down and find 36 or 30, depending where you have to round. Then I go across until I find the negative 3.17, right? I'm not going to do it that way. I'm going to use my calculator and do TCDF. Okay? So I'm going to do TCDF. It's TCDF, lower, upper degrees of freedom. Okay? So I'm going to do TCDF. Where's my face at? And since it's not equal to, I need to find the lower and the upper. So I'm going to find my lower and times it by 2. So I'm going to do negative 99999. Negative 3.17. My degrees of freedom are 36, right? 37 minus 1. So I'm going to grab my calculator. Can you guys see it? I'm going to go second distribution TCDF. Oh, I'm going to do negative 99999. Negative 3.17. Degrees of freedom are 36, right? If you don't have it that way, it'll look like this. I got point. That gave me 0.0016. Now that's just one tail. Because it's not equal to, I need to find both tails. So I'm going to need to times that by 2. Gives me point. I didn't round when I plugged in my calculator, so I got 0.031. So my p-value is 0.003. All right, there we go. Let's see what they got. Let's see if we match. Yes, we matched. Oh, so if you use the table, you got between 0.0025 and 0.001. For one tail, you'd have to times that by 2. That's not very accurate. Between 0.002 and 0.005, we got 0.003. That's good. It's using the table, not very accurate. Let's see, calculations. That's not right. They showed that incorrectly. 0.17. They just found it if it was bigger than it. So we're fine. We're fine. We did it accurately. Again, these are calc keystrokes. They times it by 2 because it's a 2-tail. It's not equal to not just a 1-tail. All right, cool. Don't forget the 4-step process. It doesn't change. State plan, do, conclude. I'm not going to spend a lot of time on this. State what you're looking for, your null hypothesis. Plan, check your conditions. Do, find your test statistic and find your p-value. And conclude, make a conclusion in context. Like always, here's why you need the test. Random lets you know that your X bar is accurate. So that number 1 is good. 2 lets you know that T will work when you plug it into TCDF. 10% will let you use the standard deviation. It's going to be a 1 sample t-test for mean. Make sure you're finding the correct t's. If it's a 2-tail, make sure you times it by 2. Let's put it all together. Let's do one. Yeah. All right, so we're looking at dissolved oxygen in a stream. They took 15 samples randomly. They want to see if it's below 5 because that'll put aquatic life at risk. We're going to do alpha at 0.05 significance level. And we'll talk about errors at the end too. All right, let's state, plan, do. So first we're going to state our null is 5. Our alternative hypothesis is less than 5 because if we reject the null, it means that it's probably not safe for aquatic life. And that's what we're trying to find out. Mu is the true mean of DO in the stream, and don't forget to use alpha as 5. So if our P level is going to be greater than 0.05, it means that we're going to fail to reject. If it's less than 0.05, we will reject the null and accept the alternative, and not accept it, but the water is probably not safe. So we need to plan 1 sample t-test for mean. Is it random? Yeah. Is it 10%? Yeah, I'm guessing there's a lot more than that. Our sample, it looks normal, so it is normal. Let's do now. This is what I want. I didn't want to do this. So here's our mean. Here's our mean and standard deviation. Now for our test statistic, T, we're going to plug in our mean of our sample. Minus our null hypothesis all over our standard deviation over our sample size, right? So when we do that, we get something. We get T equals negative 0.94. And we have our degrees of freedom as N minus 1, so our sample size minus 1, that's 14. Okay, from here we can use the table, or, oh my gosh, I'm falling off my kneelings thing. Or I'm going to use, so that's my test statistic, I'm going to do TCDF. It's less than, so I'm going to go 9999999 to negative 0.94, and my degrees of freedom are 14, right? I'm going to make sure they're right. This time we will not multiply by 2 because we're just looking at 1 tail. And I got, my P is going to be 0.182. Let's see what they got. 0.182. If you use a table, you get, oopsie, a really bad answer, so who cares? That's a negative. And let's make a conclusion then. Now, because our p-value, probability of getting that result, is over 5%, we fail to reject the null. We don't have convincing evidence that the true mean is less than 5 milligrams per liter. There we go. I want to talk more about errors later. Whoa, whoa, whoa. Alright, don't forget to show your work, guys. If you just give statistics, they won't give you credit. Please write the procedure you're doing. You can even show your steps you put in your calculator. That's all I got for you. Have a great day, guys.